Let's do some practice. We're going to do one population growth, one quick little bit of theory, and then one radioactive decay problem. Okay. 2 months ago, you started with 4 mice. You now have 28. That's all we need to model some mice reproduction. Right? Well, maybe I'll do it all down here. Let T equal number of months after 2 months ago. And P of T equal number of mice at time T. Okay. So, sure enough, P of 0 equals 4, and P of 2 equals 28. All right. Well, that means that we have P of 28 equals 4 e to the, what is that, 2k, and that equals 28. And we want to solve for k. Okay? Well, that's going to mean that either 2k equals 7, which implies that k equals 1/2 ln of 7. Okay. So now that we've got that, let's answer questions number 1 and 2. Right? This was number 1. How many mice will there be after 10 years? Now let's be a little careful. 10 years. Right? So how many months is that? That's 120 months. After 10 years, there will be... the answer is a lot, by the way. P of 120... Oh, shoot, sorry. I didn't actually even write the model. Let me scoot this down really quickly. Make sure I answer my own question. Right, so P of T equals 4 e to the 1/2 ln of 7 t. There you go. So P of 120 is going to equal this monstrosity. It'd be interesting to see if this is more than the number of people in the world. I'm sure it will be. Let's just do this one really quickly. Just for entertainment purposes. All right, let's see what we get. We get 4 e to the 1/2 ln of 7. That's a pretty big number. And actually, no, see, that's annoying. It does this. Let's, instead of just doing 0.5, I'm just going to do 0.5 times 120, 60. Oh, 10 to the 51st power. Wow. It's like more than the number of atoms on Earth or something like that. Ridiculous. So maybe we realized some of the limitations of the exponential model, right? Populations can't get over the carrying capacity of the Earth. So there are other models that address this sort of thing, more complicated and useful models. But in the short term, exponential can be nice. Anyway, how long will it take to have 10,000 mice? Not too long, apparently. All right, all we're going to do is we're going to let P of T equal 10,000. And we're just going to solve for T. All right, that's all we're going to do. This is 2,500. Right, and I'm just going to do a little bit of mental math here, hopefully correctly. I think we're getting that this is going to be 2 ln of 2,500 over ln of 7. So that long. So months, and just to be clear, months from the beginning. not from right now, because right now was 2 months later. Okay. So that's an exponential growth problem right there, okay? Now here's a quick little theoretical problem. Which of these functions show growth and which show decay? See if we can figure out why. Take a sec to look. Maybe pause this video. So here's what I'm looking at. Because that's your answer right there. Those are both growth. P of T models growth. Because, how do we know? K is positive. P of T models decay because K is negative. Just to be clear, for number 3, in case you don't see that K is greater than 0, just note that we have, this is the same as 5, e to the ln of 1.01 t. Right? So the fact that each of those yellow highlighted things is either greater than or less than 1, that determines whether K is greater than or less than 0. Okay? And similarly, this guy is e to the ln of 0.99 t. Okay. So there you go. Moving on to decay. Take some medication. Right, the half-life of medication, same sort of thing, amount of time it takes for the body to purge half of it or retain only half of it. So it looks like we start with 100 milligrams. 5 hours later, we have a little less than half in the system. So we create a model, find the half-life, and then find how long it takes till there's really a small amount of ibuprofen in there, right? And hopefully you know the drill by now, right? This is the number of hours after, I would say, taking ibuprofen. And P of T equals the amount of ibuprofen in your system okay? So, modeling approach, the same sort of thing. So, P of 0 equals 100, and P of 5 equals 40. Right? So, we're going to get P of, I guess we'll say 5 equals 100 e to the 5k, which equals 40. And actually, we'll erase that and just say that equals that, right? So we get e to the 5k equals 2/5, or you could say 0.4 if you want. And this implies that k equals 1/5. Well, that's yucky. 1/5 ln of 2/5. Ugh. Right? So that means that P of T equals 100 e to the this guy, and there we go. All right, to answer the second part, right, use your previous answer to find the half-life, right? So, let's just number these guys, right? So to find the half-life, we want to let P of T equal half the amount we started with. Whoop, equal 50, not 500. So, right, I guess we've got e to the 1/5 2/5 t equals 1/2. And that implies that t equals 5 ln of 1/2. Again, I'm skipping a bunch of steps here. So if you find any mistakes, let me know. And they say, how long will it take until there's only 1 milligram? We're going to let P of t, right, same exact thing, except we're letting it equal 1. Right? So maybe you can tell, maybe you can see where we're going, but the only difference I think should be, not k, but t should equal 5 ln, but instead of 1/2, it should be 1/100th. Okay, and you can figure out how many minutes that is. And that's what we've got. Thanks.